So, this is the part of our course which is very important, other than what we have discussed about the active faults and fluvial landforms and coastal landforms. Now, with the understanding of the coastal landforms, let us see that how best we can interpret or identify the signature of paleo earthquakes. And when I am talking about the paleo earthquakes along the coastal region, signature of the paleo earthquakes around the coastal region, that means that we are talking about mega earthquakes and large earthquakes. So, mega earthquakes are those earthquakes which along the subduction zone which have the magnitude of more than 9 and less than 9.5. So, and of course, the large earthquakes can range between 7.5 and 8.5. So, we are talking about those signatures of those earthquakes. So, I will also try to highlight here, if time permits, the recent research which of our team got published in Nature Scientific Report, where we have been able to identify 7 tsunamis from the record of the past 8,000 years from Andaman. Now, with the introduction of the tsunamis, mostly in the literature you will find this picture from Japan, but this picture it was drawn or created by the Hokusai in year 1829 and 1833, and mostly this is getting like it is mistaken with the tsunami waves, but of course the tsunami waves are deadly, and some of them have interpreted that the tsunami waves are so deadly that they have the claw here which can eat away the landforms and the settlements, and it could be much larger than Mount Fuji also. So, although it is often used in tsunami literature, there is no reason to suspect that Hokusai intended it to be interpreted in that way. Okay. The waves in this work are sometimes mistakenly referred as tsunami, but they are more accurately called okinami, great offshore waves. So, of course, the great offshore waves, if we consider, they are referred as tsunami, and the tsunami word itself comes from Japanese side, that is the harbor waves. Okay. So, tsunami is a Japanese word meaning harbor wave, or a giant wave or big wave, you can say. The height of this waves is small and barely noticed in the deep ocean, and this is because of its larger wavelength, but becomes larger and damaging when they approaches the coast, and this is because of the stacking when they enter into the shallow waters. You will see this one. Okay. So, please keep in mind that what we discussed about the crust and the trough here. So, we will talk about the wavelength here like this. Okay. So, this wavelength will be extremely large in the ocean. So, you won't be able to even notice this. So, if you are having a very large wavelength and very shallow, so even if you are having a ship or a boat sailing on this, it will just sail very smoothly. Okay. So, no worries about that in the deep ocean, but when it approaches the coast, it is extremely damaging. The wavelength could be more than 200 kilometers and very shallow, that is the crust will not be so high, hence it will be barely noticeable in the ocean in the deeper waters, but when it comes to the shallower waters, the wavelength decreases and the height increases. Okay. Hence, it will be more deadly when we are talking in terms of the amplitude. So, I do not know whether it will work or not, but we will try. Okay. So, now if you look at this small movie, that shows that how usually the two plates, the one that is along the subduction zone, the oceanic plate is subducting below the continental plate, or the oceanic plate subducting below the oceanic plate, then what will happen? Because these two plates, when they are having the area of the interface will provide a great friction, and they will keep having like an accumulation of strain, and due to the accumulation of strain the rocks will get deformed, and it will result into the deformation of the landforms near the coast or along the trench area. So, and then when it slips, this will disturb the water column sitting at the top of the displacement here, and that will result into the generation of tsunami waves. So, tsunami waves are considered as a secondary phenomena related to earthquake. So, tsunami waves can also form because of the submarine landslide. If you are there is any slip or the landslip material is poured down into the ocean along the coastline, then that can also generate the tsunamis. But those tsunamis will be local tsunami, will not have very wide effect in terms of the area. But if you are having the tsunamis triggered along because of the earthquake and the displacement between the two plates, then it will have the wider effect covering or affecting larger areas. So, and sometime it so happened that the displacement in terms of the length, that is the source, is less, but then if it is connected with the or it get associated with the landslide or submarine landslide, then the waves are much larger, which sometime is unexpected. Okay. And the same thing happened during the 2011 Tohoku earthquake. The rupture length was around 500 kilometers in terms of the length, but the waves which were been experienced were much higher than what it was expected, and that was because of the submarine landslide. So, let us see what usually happens. So, just keep eye over here, and then what happens here, and then what sort of a land level change takes place here, and after the slip here, how the waves are generated. So, slowly the plate is moving down here. This is the portion of locked area. So, this portion does not slip, but it will keep on dipping up like this. The area is getting down. So, it subsided, and then when it was unlocked or slipped, then the area was uplifted. So, you can see this portion, the orange portion has been exposed, but earlier only this portion was exposed, but this went down. Okay. So, I will play it again, and then you can find out. Now, one important point which I would like to mention here is that if you are having GPS stations across this one in this area, then you will be able to fix up that the area is subsiding over a period of time, and that is also in a case you can warn the people that this area can slip in future and can have. So, if you are having the subsidence periods which goes or uplift period in some area is much larger, than we are accumulating more strain, and we can have much larger earthquake in that region. The early warning systems and all that, they work based on the tidal gauge records, and this tidal gauge record is from Japan, but the tides which were been unusual tides which were been recorded was not an earthquake which was triggered along the Japanese subduction zone, but this was because of the subduction zone which lies between the Nazca plate and the South American plate in Chile, along Chile. So, this was the 1960 Chilean earthquake, one of the largest so far recorded earthquake on the earth. That was magnitude 9.5. This was one of the largest recorded earthquake, and so what it shows, this tidal gauge, that this is they have the curve which shows the mean tide level. So, you have the high tide, low tide, high tide, low tide, and all that, but suddenly they had some which is shooted up in this. So, this portion of the unusual record of the tidal waves was because of the 1960 Chilean earthquake. Now, one thing which we can think of that the Chile or the subduction zone, Chilean subduction zone lies much far from the Japanese coast, but the effect of the tsunami was experienced in Japan, which is sitting very far away. So, this type of tsunamis, we call this as an trans-oceanic tsunamis. So, they travel across the oceans and cover larger areas. Tsunamis are basically the long water waves generated by sudden displacement underwater. Tsunami is always also termed as seismic sea waves, and they are a series of waves generated by large violent earthquakes occurring near the ocean. Not all earthquakes will generate tsunamis, because this again depends on the amount of displacement and displacement of the water column. But the most destructive tsunamis are generated from large shallow earthquakes with an epicenter or the fault line near or on the ocean floor. It depends on the displacement and also the depth, at what depth it has been triggered. Okay. So, if you are having shallow earthquakes, then you will have larger tsunamis. Now, if we compare this with the normal sea waves and the tsunami waves, then normal sea waves, the sea waves we call tidal waves, are because of the attraction or the gravitational attraction of moon and sun. So, and they will have the wavelength which is ranging to 1.1 kilometers, but whereas in this case it can attain more than like the wavelengths may be up to 100 miles or more. Okay. So, you and also the speed at which it travels, it will travel at the speed of jet, almost like 800 kilometers per hour, whereas here it will have only few miles an hour or so. Okay. And these are generated because of the earthquake. So, these are the major difference between the normal sea waves or tidal waves and the tsunami waves. So, usually in tsunami, what it has been experienced that not the first wave can be more powerful one, okay, because it may be the next wave which is coming in could be much more powerful than the first wave. Okay. The duration of the wave action is as long as several minutes to around 10 minutes long. Okay. And this depends on its wavelength. Okay. That what is the wavelength of the tsunami wave which is generated. And suppose sometime you have people have experienced that, and reports are there that the first wave was not the positive wave. When I say the positive wave, then we usually talk about that this is your positive and this is your negative wave. So, the first wave, if it is positive, then it will inundate, but if it is negative, then it will expose the coastal region. Okay. So, in some cases, the local people, survivors, they experience that the ocean flow for kilometers, and then it got inundated because of the arrival of the next wave. Now, narrowed bay levels of tsunami. So, this configuration of the coastline will play an important role. So, when we try to prepare the inundation maps and all that, so such features or the landforms are been targeted, where we can have the high tide the high tide level of tsunami because of its topography. So, it hits as fast as aircraft or bullet train. So, the energy the velocity is much higher as compared to the normal sea waves. Why tsunami are so destructive? This is what we were talking about, that it is barely noticeable the deeper portion of the ocean, whereas as it comes closer, then the wavelength reduces, but the height increases because of the stacking. So, as the tsunami waves enters the shallow waters near the coast, its velocity decreases, its height increases. Okay. So, basically because of the stacking, and the height may go up to 30 to 50 meters depending on the topography or the configuration, the geomorphology setting of the coastline. This is the photograph which shows wave height and the two waves coming in here during the after the 2004 earthquake in Thailand. So, height and run up is another important factor which is been taken into consideration for modeling or simulation of tsunami waves, as well as preparation of the inundation maps or tsunami hazard maps. So, the height or the run up of the tsunami at the point of impact will depend on, one, how the energy is focused. So, what is the alignment of your coast with respect to the tsunami waves coming in. So, suppose you are having this here, then it goes like that. Okay. So, what we were talking about, the relationship between the wave action. Okay. So, we that whether the waves are diffracted or refracted from the along the coastline. Then the travel path of the waves, how they are traveling, from which direction it is coming, the coastal configuration, that is the geomorphology of the coast, and the offshore topography. Tsunami run up is the vertical distance between the maximum height reached the water on shore and the mean sea level surface. Okay. So, if you are having the mean sea level here, MSL, and the water which reached up to this point on the mainland, then this will be your the run up maximum height, okay, of the run up between the mean sea level the wave reached, okay, up to the point inland. If you consider this, then what it shows that you have the A is your measured height, okay, and B is your tidal difference at tsunami, or that is tidal difference between the time of the tsunami and at time of the measurement. Okay. So, at the time of the tsunami, for example, you had the sea level was this one. This is because of the tidal fluctuation, okay, not because of any other reason, because the sea level remained the same. So, if you were having the sea level at this point, for example, there is a low tide, and then at the time of the measurement, then you will have to take into consideration this. So, you will add this plus the height you have measured, that is your A at the time of your survey. That will give you the total height of the tsunami. This is a common practice which we do after the tsunami in any area, to understand that how much area got affected or what was the run up height and all that. So, we try to look at, because when the tsunami wave comes, it will try to wound the trees along the coast, and also leave the watermark if you are having any buildings. Okay. And also because waves enter and run up will be up on the inland side, then it will also leave some signatures of the material which is carried, for example, the debris. Okay. So, plant debris also can be seen sitting at very higher level, depending on that what was the run up. Okay. So, this type of signatures we try to collect, and then we measure we take the topographic heights and all that, and then we identify mainly the height of the tsunami. Okay. So, these are been used as height of tsunami indicators. So, if you look at these two photographs from Indonesia, which was the photograph A on the left is before and B is after. So, you can just correlate these two houses which are left out here, but rest of all got destroyed and wiped off. So, the inundation maps, which when we are preparing, we take into consideration the run up heights from different tsunami, or the lessons we learn from the past tsunamis. Okay. And so, tsunami energy, if you want to calculate, it is very easy. the total energy of the tsunami can be approximated by the equation which is given here, where E is the total energy, and then we have the density of the ocean water, usually taken at around 1.03 g per centimeter cube, and then you have the acceleration we take, okay, and then we have the assumed height. So, if you have the height, assumed height of the area where that is average height of the crustal displacement, then you can easily calculate the energy conditions of the tsunami. Okay. And A is the tsunami generated area. So, how much area was involved in generating the tsunami? That is we take so this you can get from the seismic data, which helps in fixing up the total area of rupture. So, velocity of the tsunami wave can be calculated, which depends on the water depth and the gravity. Okay. So, you have gravitational acceleration, which we were talking in the previous slide also, and where c is the velocity in meter per second, d is the depth of the water. So, for example, what you have is that if the d, that is the depth, is 4,600 kilometers in the deeper ocean, then you can have the c is equal to the Smith meter per second. Okay. So, it will be, or you can say that this is around 763 kilometers per second. So, this is almost equivalent to the some of the jet aircrafts. Okay. Now, if you are having shallow water that is near the shore, so this is the deeper portion, whereas if you are having the shallow water, then the energy conditions, like the energy reduces here. So, that is the velocity. Okay, velocity reduces, but in that the height increases. Okay. So, this is the main difference here. We are having around the deeper waters, the velocity is high, but here the velocity decreases. Okay. Now, this is an example which we will quickly look at, that what happened along the Chilean coast here during with the earthquake which was triggered along the trench or the subduction zone between the Nazca plate and the South American plate here, and how it affected and what were the signatures which they found way far away, like in Japan area. Okay. Of course, it also affected this whole ocean, that is the Pacific area got affected because of the 1960 earthquake. Now, these areas are very sensitive in terms, because these are all subduction zones, and these areas are very sensitive in triggering the large or mega tsunami. And then we are sitting here, we have the Sumatra, and then further up, if we go towards north, then we gets into the Andaman region. So, the tsunamis triggered here in North America will also affect the coastal regions which are sitting in the Pacific ring here, and if the tsunamis are triggered here, they will also affect this region. Okay. So, these are few listed tsunamis. 2004 is not listed in this, 2011 is not listed in this, and few more which were recently experienced. So, this was the great tsunami of 1960 Chilean earthquake of magnitude 9.5. So, the largest subduction zone earthquake of May 22nd, 1960 Chilean earthquake magnitude was 9.5, and then second largest we consider this as a 9.3, but in some literature you will find that the second largest earthquake has been listed as an Alaskan earthquake and from North America, and that was around 9.4 or so. So, anyway, coming with considering this was for us, it was the second largest one, the 2004 as compared to the 9.5 Chilean earthquake, the largest one. So, this is the subduction zone here, and what we are going to discuss more further is from the Sumatra Andaman subduction zone. So, the numbers which are shown here and with the white contours are the hours which took the tsunami from this point. So, 0 hours, it took almost 22 hours to reach the Japanese coast. Okay. So, in some locations you have like ample of time available to issue the warning. So, you can evacuate the people from the coastline and all that. If we look at this one, then it almost took 22 hours. Okay. So, the Chilean subduction zone is of course and very one of the deadliest subduction zone which has triggered many more tsunami, not just only 1960, but even comparatively smaller tsunamis along this one. As we have discussed in the beginning, that the earthquakes occurs when the fault ruptures and sudden release of the energy which is getting accumulated over the time is released, and if the water column has been displaced sitting on that rupture, then it will result into the tsunami. So, this the sketches also shows the similar part which we saw in the beginning, one small cartoon, but here it shows that the area, because of the locking here, will get uplifted, and then finally when it is released, it will result into the that is the energy is released, it will cause the slip here and then result into the, so slip displacement will cause the formation of the tsunami waves. So, let us look at a few examples of, from Japan and Chile, which indicated that what happened during the 1960 Chilean earthquake. So, this was the area where we did a detailed survey, and this paper was published in Nature long back. So, we did joint field with USGS scientists, and 2 of us were from India and then 2 from Indonesia. So, we had a big team, and then we worked in Maulin here. So, this photograph is from this area here, which got affected during this earthquake, and the area subsided during the 1960 Chilean earthquake, and the bridge which was sitting here was blown up. Still it is not constructed, so we used to travel through this area and reach this portion to identify the paleo-tsunami signatures. So, this was the situation in the city after the 1960 Chilean earthquake. The houses were been destroyed completely, and this photograph was been taken where we did our survey, but this was before 1960 event. So, this and then there is a river which flows here, and this whole area was a very good agricultural field, and you can see the houses and the boundaries here, the agricultural fields. So, people used to stay here. So, that means that even during the high tide, the water never used to get into this this region, but after the 1960 earthquake, this was the situation. So, you can compare these trees here. So, few trees were been left out, whereas whole area was swept away, and this shows the first wave which came in, which was only removed some structure from here, but the second wave took away the hut which was sitting here. Okay. So, this is what one can learn from that, the multiple waves will come. So, this was first wave, and then this is the second wave. Now, in Japan, what they found was that again the tidal gauge chart which I have shown in the beginning, that it was an unusual recording of the tidal height in the tidal gate station. So, this was at 4:40 a.m. The front of the first large wave which came in. So, the warning was been issued, people moved on high ground, and then you can see the second that was 4:40, this is 4:45, still the window is here, and the train station was also intact, but later on the window was pushed, and then they got a lot of debris coming in. So, this was at 4:55, but the photograph was been taken at 7:30 a.m. and this left the watermark here. So, such features or the signatures we try to take into consideration when we are talking about the run up or the tsunami heights. So, this was the area which now is subjected to inundation in Chile, and the area which was occupied earlier is under erosion, and we see the signature of the dead forest there. So, we tried to look at some signatures of the dead forest, as well as we looked at the preservation of the tsunami deposits, if at all they are present, indicating the past events. So, this was the area which was occupied earlier, but now this sits under erosion. So, people have moved on the high ground and they have started settling down on the higher elevation, because this area is affected after this. So, this is under erosion. So, what we did was that we studied the sections here, which helped us in identifying the signature or of the previous earthquakes or tsunamis. Okay. So, we used the backhoe or what we call JCB in India, and we open up the trenches and studied the stratigraphy. So, this is the team here we have. So, usually what happens is that when there is an that before, this is, for example, this is the surface here. So, you have in soil, and then you have vegetation like what we see here in this photograph, and then if the event results into subsidence, then the area has been subsided. So, this level has gone up. So, water will inundate, and when the tsunami water comes, it will carry a lot of sediments, okay. And that sediments, those sediments will get deposited and then get preserved. So, after decades you will find that there is a very prominent sand layer which is getting preserved in the stratigraphy. So, this is what we see in the section. So, this soil was 1960 soil. So, this was the surface during 1960, and then the area was subsided. So, this 1960 soil goes here, and then this was the sediments which were been brought by the tsunami waves got preserved here, and this what we find the tsunami sand. Okay. This is one of the way to identify the previous the older tsunamis, and what we found here was that multiple tsunami sand layers, okay, from this. Okay. So, we have the soil here which is humus rich, because along the coast we will have very rich organic material. So, you will have humus rich soils, and then we are having kept the sand layers which are capping those soils. Okay. So, if you have the edges of this, the sediment edges, then or edges from the charcoal found in this, then we can bracket the events, and that helps us in identifying the ancient tsunamis. So, this was like around 1000 years, then is 12,000, this is 1200 AD to 1300, then 1500 and 1960. So, this also can help us in bracketing the events, as well as we can talk about the recurrence interval. So, I will stop here, and we will continue in the next lecture talking about the part from the Indian side. Thank you so much.